It's a pleasure to be here. Thanks for having me. I'm really sorry I missed yesterday. I was teaching in Chicago, so I couldn't get here until evening time. But I'm glad to be here today. So this paper is trying to think about what AI might do, or transformative AI ultimately might do, through its work in the R&D or knowledge ideas production function. And I'm kind of motivated from this essay, in part, which inspired this January meeting that got me thinking along these lines and interested in writing something, just to read it out loud. I believe that in the AI age, we should be talking about the marginal returns to intelligence, which I thought was an interesting sort of concept, and trying to figure out what the other factors are that are complementary to intelligence and that become limiting factors when intelligence is very high. We are not used to thinking in this way, to asking how much does being smarter help with this task and on what time scale, but it seems like the right way to conceptualize a world with very powerful AI, where I think powerful AI also sort of means these servers full of cheap genius, millions of cheap geniuses running in parallel. Okay, so with that kind of remit, I wanted to think about how we might start to think about how AI capabilities, particularly around intelligence, for example, might or might not lead to massive change in our ability to progress various kinds of outcomes. And naturally, I went to a task model to think about this. We can imagine there's some automated tasks and some labor tasks, and so there's some fraction that are done by machines, which would include AI. And of course, there's a big literature going way back, and Pascal has, of course, done incredibly important work in this space, among many others. I want to say that where I'm going to go here is that there's sort of a share of tasks that are done by machines, which is going to be very important, but also there's how good you are at tasks, which is something more from my work with Ajay, where I want to bring in this sort of, that's where the intelligence would be. We want, really smart servers, we can't just think about the share of what you do, but also how good you are at it and how much that does or does not make a difference. Okay, so the paper is basically going to take that kind of approach and apply it to research and development. And it's going to be micro, in part for the reason that I want to be sort of broad in the application areas we might think of, right? So we often think about these models of tasks in general equilibrium, or with, TFP growth maybe as the ultimate outcome. But of course, we also care a lot about health, for example, and we might really care about how AI and R&D could sort of solve cancer or various other kinds of issues. And we want to think about it as part of product development, and we want to think about it at the sort of productivity or profits of a particular firm, or how you would do entrepreneurship as a sort of, with AI or something. So I wanted to kind of be a little bit open. And so in other words, what I'm going to do is I'm going to imagine that you have some generic outcome Z, which is the thing you want to improve. So that could be, for example, very narrow, like I want to determine the shape of a given protein, or at least the folds. That'd be like AlphaFold. Maybe it's broader. That's sort of part of a broader set of tasks that would make me come up with a drug therapy that would solve a particular cancer. Or maybe I want to think about Z as like super broad, like how long do we get to live in the world? Or similarly, you could do the productivity of a firm in a particular sector, to an industry, to a TFP. You could think about this narrowly or broadly. And then for any given outcome, once you've decided what that outcome you care about is, like drug therapeutics, then you would have a set of tasks that would be relevant to that research outcome that you would undertake, that could either be done by AI or labor or some other machine. And then we want to bring in the idea that AI is going to sort of radically improve. Okay, so that's what the framework is for. And I want to ask a bunch of questions, and maybe some others. It's like, what is the effect of large advances in AI? Is transformative AI possible? Like, what would be the mapping you need between sort of AI capabilities advance to actually give you that kind of TAI-like outcome? What would this powerful AI do, meaning like millions of geniuses in a server? And then what is the marginal return to intelligence? Okay, so I'm giving a very simple framework in a sense. It's going to leave out things that I think are probably important. At the same time, I mean to sort of get us focused on three things that are in the framework that I think you kind of have to address. Maybe there are other things you need to address, but I think if you want to take a stand on this, you really have to address these three things, which are: first, what is the fraction or share of tasks that the AI will do in the research process? I'm going to call that gamma, 10%, 40%, 90%. How good is AI at these tasks? In my model, that's going to be cap M. It's kind of a measure of machine productivity on average, okay? And then how strong are bottlenecks, which is, we could think about from like a CES parameter or from a generalized mean parameter. That's how I'm going to think about it. We'll call that theta, okay? I also want to say, so I'm going to just basically do conceptualizations, kind of abstract conceptualizations, and see what you have to believe to get from AI to TAI or whatever. But I also believe this can also form a measurement agenda, because I'm going to say that these three objects are like the three things you need to know if you were going to try to make a strong claim empirically. Okay. So this is very standard. I don't want to show you lots of equations, and so the only thing that's different here is that equation one, normally on the left-hand side we put y for like output or GDP. Here I'm putting z dot, so it's an ideas production function. So it's a function of, do I have a pointer? I don't. So z dot is just like, z is my longevity if I get a given cancer, and z dot would be like how much longer I want to live. Z is the current state of knowledge at that. That's actually, I'm going to kind of ignore all of that kind of longer run implication between how the state of knowledge affects your rate of progress, very important in macro models. But here I'm going to really just look at your sort of short run. If I just surge AI's capabilities, in which case ZT is fixed, like how much faster am I going to go, at least in the short run? I'd also argue that in a lot of contexts, the short run is going to be the upper bound on how fast you're going to go. All right, and then the next thing in brackets is just your standard aggregator, where the little r's are your tasks, your research tasks, so R. Okay, so go down the line, standard stuff. The task can be performed either by machines, which have, like, on any given task J, you're going to have a machine productivity M using some capital input X, or you could do it with a human, in which case you have some human capital H, and you apply some labor little l. H, I'll just keep it constant across all the tasks just for simplicity. You could have a lot of heterogeneity in how good the machines are at different tasks, okay? And then machine tasks, this sort of key parameter that's going to emerge here. So you could think of it as a parameter, you could think of it as endogenous, depending on how you do this model, but gamma. So some fraction of tasks can be done by the machines, and the rest, 1 minus gamma, is going to be done by labor, okay? I'm micro, so I'm taking prices as given. There's some price of using a machine, there's some price of labor, just for now. Now, that's important, right? Because the excitement about AI can really be twofold. It's that its M might be really high at a task. Wow, it's really good at that. And a lot of our kind of gee whiz AI stuff is like, wow, look what it can do, and all these things we ask it to do. But of course, the other piece is that the mu, the cost of using AI, can be a lot less than the cost of using labor, W. So a lot of the kind of relative gain you can get from an AI is that it's also really cheap, for whatever task you are giving it. Okay, and then theta up in the top there, right? That looks like a relative, like the CES parameter, but theta written this way, right? It's also the generalized mean parameter. So theta is 1. Like, that's perfect substitutes, right? Infinite elasticity substitution. But theta is 1 is just, you're just adding up all the r's. Just make theta 1. That's just, and each one weighted by di. That's just the arithmetic mean of all your task outputs. Okay? And in that world, if you made one of your tasks like really, really productive, in an arithmetic mean, when one variable goes way up, the whole thing goes way up. It's pulling very strongly upward on progress. But if theta is less than 0, which is the case I'm going to look at, and I'm going to argue later that, well, the empirical evidence is not fully developed by any means, that's probably a better assumption, then that's where bottlenecks start to come in, right? So if theta is -1, it's the harmonic mean, okay, which you may recognize. And harmonic means, for example, are like brutal, and they're getting you close to Leontief, which is, of course, theta is -infinity. Then all that matters is the thing you're bad at, and bottlenecks matter, a theme that keeps coming up, and Susan was just talking about as well. Okay, so I'll come back to that. And okay, so then again, this is like pretty much the only equation I'm going to show you, and it's not important that you really address it. I just want to set up what's the problem I'm answering with the theory, and what am I not answering. So I'm saying, imagine you have a given R&D budget, like you have $1 to spend in R&D, and you could either hire labor or you could hire machines, and you're going to allocate that across the tasks. Okay, so the optimization problem here is simply that you're going to say there's these M's telling us how good the machines are right now. There's this H for humans. There's some prices for AI and labor. That's the mu and the omega, and I'm just going to optimize my allocation of $1 of R&D spend to kind of give me the fastest rate of progress I can get for that $1. Okay, so what is that? And that's what it turns out to be, but don't worry about it. It doesn't really matter the form. I just want to point out that, like, so if you increase a dollar of R&D, you get some more Z dot. Here it's linear because I haven't had any congestion, but we could do that too. But the important thing is that's kind of like a return, right? So I put $1 of R&D in, I've optimized my allocation, how much Z dot do I get out? You could literally make it a return if you put Z dot in dollar terms. Like if it was health and you attached like a quality and then you had like a value of statistical life, you could sort of say, okay, I put $1 in, that's what I get. Or maybe a productivity sense, I get some value added on Z dot, and then I put some money into R&D. That gives you a real return, okay? So think of a private return. The other point is in my last bullet here is that by increasing AI capabilities, we can see how we change that marginal return. What's the marginal return to intelligence? For a dollar I put in, I get this much Z dot. If I take up M radically, now what's the return? Okay, so we can think of it that way. So here, as you can see, I'm trying to answer the marginal returns to intelligence question. Last point is there's a cap M now. The big M is basically an average of all the little m's. Okay, but it's a generalized average again. It's not arithmetic average, so it's going to depend on bottlenecks. Okay, all right. So that's kind of summarizing. All right, now it turns out, so let's go to the first question. What happens if you radically increase machine intelligence, by which I mean M? Now this is actually maybe not what we mean, so just be careful what I mean here. There's actually two kinds of AI capabilities here, right? There's sort of how good are you at the tasks the AI does, M, but there's also how many or what share of tasks does the AI do. So what I'm going to just do here in this thought experiment is I'm going to hold the share fixed. It's whatever it is, and now I'm just going to take you to like as far as you want to go in terms of your M. And then in a minute I'm going to do the other thing. I'm going to expand your share of tasks you can do, all right? So fix the share of tasks, now let M get bigger, okay? Defined by lambda, some multiple, okay? It turns out that this theory allows you to kind of think about things in ratios, and so I actually don't have to take a stand on what M is right now, or any of the little m's, or what H is, or even what the prices are, because it turns out it all gets summarized in SXT, which is the current expenditure share on machines as opposed to labor out of your dollar of R&D. Okay, so that turns out to be like a little cheat code for empirically. So if you think something about SXT, and maybe Bronwyn may talk more about this, then all you care about is lambda, which is how much I multiply your average productivity, and B, which is just a function of theta. So you have to take a stand on your bottlenecks parameter. Okay, so that's an equation that comes out. It's actually sort of simpler to execute than you might think, because we can just sort of use this cheat code of the expenditure share on machines. So I'm going to take that as the third in the following graph, and maybe that's too high, but we can talk about that, for different values of theta. So what am I doing on the x-axis? I'm multiplying theta by a lot. Like this is logs, 10, 100, 1,000, a million on the right. And this is the rate at which z dot multiplies linearly. Okay? You can see that if theta is low, like take theta -1, that's the red line in the middle, you're actually capping out at just over 2. So you could get like infinitely intelligent machines operating on the current set of tasks, and you multiply the rate of progress by 2. So it's very modest, because theta is equal to -1, harmonic averages, again, are brutal on bottlenecks. The point is that it doesn't really matter how good you get at this, because the bottlenecks, the things you're doing with labor, or maybe other machines that aren't AI, are holding you back, okay? All right, but again, I'm also not letting you expand the share of things that the AI does, and I think we're also trying to imagine maybe these smart servers full of AI now take on a lot more tasks from labor. Okay, so what does that look like? Well, it's a different equation, but I want to show it to you. Then you get this result. Okay, so here what I'm doing on the x-axis, chi, is what percentage of labor tasks are still done by labor. Okay, so like 10 to the -1 is you've already gone to like the AI does 90% of the labor tasks. 10 to the -2 is the AI does 99% of all the labor tasks. So and I'm expanding that. So it's whatever we're doing now, it just takes over 90%, 99%, 99.9%. Okay, but I'm not letting you get smart. Okay, I'm holding MT fixed. So I'm saying whatever the current state of sort of smartness is, so this is not your geniuses and servers, I'm just going to extend that across everything. And then you can see that, again, if theta is -1 or something low, you actually are capping out at pretty low multiples. Okay, and the point is that basically what this is assuming is that the machines, sort of aren't really that good in some sense. So if we just switch to machines and sort of the productivity versus cost of machines isn't so great, then you don't get that much of an advantage, per dollar spent. Remember, this is not general equilibrium. The other thing that could happen here is you would say, oh, I'll spend more money on R&D, as you are getting more productive at R&D per dollar spent, so you might say, oh, well, there's going to be another kind of quantity effect, scaling effect, which may happen. Of course, a lot of R&D in the Americas is being cut, even though it seems very valuable. So it's like, it's the market failures, and it's not entirely clear that we get our normal sort of, endogenous equilibrium going all the time without the political economy, thinking about the political economy. Anyway, okay, so where are we? So it seems like if you just get really smart machines or you just get really massive expansion of tasks, that's not actually multiplying. I mean, twice as fast isn't bad, but it's not like what you might think. And of course, the answer to what's going on here is bottlenecks. It also means that you want to really think about any kind of massive gains that we're going to get from AI. You have to really expand on both margins. You need to do both, lots more tasks, and you have to get really good at them. Okay, so what's going on is because bottlenecks are brutal, and I think the simple math that I like about bottlenecks is if theta is equal to -1, what's the harmonic average of the number 1 and infinity? It's 2, okay? And that's sort of what's happening in the model. The arithmetic average of 1 and infinity is infinity, okay? But in Leontief is 1 of infinity is 1, right? But as soon as you get to theta less than 0, you're really just kind of muting sort of how good you are at certain things and not others. And I would argue that Moore's law, we have 10 to the 17th more floating point operations per dollar today is kind of a real world version of this. Like we've basically gone to a more or less infinity in a lot of tasks. And we don't use computers for one task. We use them like all over the place, right? And not that in every software application it's that good, but like think about a regression. Think how much faster you run a regression with 1 million observations than you would yourself. You spend your whole life inverting one big data regression coefficient matrix, and you get it wrong. Also, I get it wrong anyway. Maybe you're better than I am, right? And so the gain in sort of productivity on running regressions for economists is basically infinity. I mean, it's like unbelievable. It happens in like a minute with a cheap computer, right? But obviously, economics hasn't our level of insight is probably improved, and we probably hopefully move faster than we did before. But we haven't gone to I don't know, you guys. I don't know how fast we go, but it's not as impressive, right? So this is all bottleneck stories. Are bottlenecks reasonable? So I had this completely different paper about how you assess credit in teams that looked at what happens when you take a bunch of people together and you do the fixed effects where they move across, like us, you move across papers, inventors move across patents, and then you try to estimate that theta parameter in a CES production function. And when you do that, basically, what's the median when you do it across hundreds of science fields and hundreds of patent fields? It's actually -1 or maybe slightly less than that. So I mean, this is not machines versus humans, but it's somehow, it's different inputs into the same production function. People are probably doing specialized things. It looks like theta is equal to -1. Amdahl's law in computer science. If they're computer scientists here, they get really excited. Neil, you're getting excited, right? Amdahl's law is like this kind of main idea in computer science that the overall performance of the system, how does it relate to the component performances? And guess what? It's the harmonic average. It's negative. Amdahl's law is -1. You can do various thought experiments. And the second one I think is again we kind of got at, and which is that regressions are kind of an amazing advance for economists, right? But a lot of other fields have this: telescopes, microscopes, X-ray spectrometry. There's so many machines that we use that their sort of comparison to human senses of observation are basically infinitely better, right? And they've given us enormous insight empirically, but somehow that hasn't necessarily I think it's very helpful, but it hasn't radically shifted the rate at which we understand cosmology. Particle accelerators, I don't know if Brian will talk about particle accelerators, but that's another great example. And when you see that, over important tasks that we do in our research, massive increases in productivity, but sort of more limited and muted overall progress, that's a strong indication that we're sort of in the harmonic average land, not in the arithmetic or even geometric average land. TAI, but you can get there, okay? And when you do both margins, you can get there, because if this is sort of what share do you replace? So now you're down to 0.2. That means that the AI is doing 80% of all the human research tasks. And then this is kind of logs on M, like how smart are these machines, your powerful AI. If you can do a lot of automation and you have smart machines, it gets better. In fact, if you can get to 80% automation, even with theta -1, and your machines are only 10 times as good on average, then you actually multiply it by 10. My line here is when you get 10x, is one definition of transformative AI, increases in the rate of progress. That said, so I think it is probably possible, but this is only one research outcome. The world is a bunch of different Z's, right? And if you thought about TFP in the real economy, we think about bottlenecks, chips, or whatever was one example. But in macro, we think of the elastic substitution as 0.5 between capital and labor, which incidentally, by the way, that's theta equal to -1 if you convert it. And in health, obviously your health is not the average function of your organs. sadly, right? Many are the ways we can fail, right? And that's a low theta health system. So we can have radical improvements on some things. Maybe we solve cancer, but if we don't solve all the cardiovascular issues or chronic pain or mental illness, where are we? So there's just much, much more to do. And so I think that actually gives you kind of a nested, so there's the bottlenecks within a given research process to improve, like come up with a drug for that thing. And then there's like, well, you got to do it across all these other things. And so you're going to kind of run into the second layer, which makes me think about what you guys were doing in terms of networks of production functions and things. And but also maybe they're end routes, but that you can get around and substitute. But it does suggest that it's complicated. So I'm going to try to coin a phrase. I will fail. Economically meaningful AI, EAI. And I'm only going to say that because I know we're supposed to only talk about TAI. But if you think TAI is difficult, and then we're like, AI, what does it do anyway? I mean, TAI is like incredible. What I'm going to call economically meaningful AI, which I define in the paper as like 1.5 times progress. That's like much more feasible. And if you add it up over time, you get to somewhere very, very, very profound.
Is that 1.5 in levels or rate?
Rate. So if TAI is 10x the rate, if I back up to 1.5, obviously if I lower it, it's more easy, and I can get much nicer diagram here. But also, 1.5 times the rate of progress since the Industrial Revolution going forward, that's 3 industrial revolutions in 150 years. It's who knows what technology, they can't even imagine them. I think the median real income of the US household becomes $4.5 million. I mean, so these are like, it's hard to imagine what we're even talking about, and that's just economically meaningful AI, not TAI. Okay, last point, and I should stop, is that I also think there's a measurement agenda here. You guys were very helpful in terms of helping me think about benchmarks. So I'm keeping to come back to you, but it's coming together very late. So, AI loves benchmarks, right? Because you measure how you're doing, you compare the different models, but also you train to sort of beat those benchmarks, right? It's a very, very central part, and there are many, many, many of them. So it turns out that the parameters, like the share of tasks, how good you are at tasks relative to humans, and then the bottleneck parameter would give you a way in any particular research area with a benchmark design to, in fact, estimate these parameters in the context of some real research application. And in fact, PaperBench, which is one of them, does that. PaperBench is like, the outcome is, can you replicate these ML papers? So it's kind of like a real research task, not just like, can you solve a math problem? They then code like 8,000 subtasks, right? That you have to do. Then they have the AIs do them all, as well as the humans. The AI is better at only some of them. That gives you a kind of a gamma, potentially. What share would the AI do? You can see how much better it is at those, because if you know just how much time it takes a human, how much time it takes the AI, you get very simple measures related to the model. And then you can get theta just by experimental variation of inputs and outputs to see theta in a given area. Anyway, so I think that there's a way to take this framework and apply it in benchmarking, or maybe design benchmarks to fit this framework, where you can say not just like, wow, gee whiz, it can solve the math problem, but like, will it really radically accelerate progress in what area? I think it probably varies highly across different areas, like pure math, software design, drug design, might be wildly different with these parameters in a way that would be that could be enlightening. Okay, sorry to go on a little long, but thank you.
Thanks very much.
So I think I am probably the only person in the room who actually has run a regression on a Marchand calculator, using from a cross-products matrix. Yes, but fortunately that didn't last very long. That was almost my first job when I was working as a research assistant for Sri Grillicus, was checking a cross-product inversion for a regression. Okay, so which one goes? The green probably goes. Well, first of all, I really enjoyed this paper. I have to thank the organizers so much for inviting me to discuss it. I liked thinking about it and so forth. We know what the core question is, so I won't repeat it. And his approach is, this model is really very elegant. I really like it. He talked during the presentation enormously about the bottleneck side, and I have no disputes with that. I think that's a very interesting thing to focus on and so forth. I had some reservations about the model, which I spent a lot of time on. I am now more or less satisfied, but my discussion basically has 3 parts. One is just to tell you briefly why I was puzzled with the model, because I think there's a limit to what it can do because of the fact that these M and the gamma, the average productivity of the machines and the share that they're used for are actually jointly determined in the model from the primitives, which are really the individual machine productivities and the cost of the machines, as well as the labor productivity and cost. And the net result is that if you really, wanted to take a derivative with respect to gamma, it's buried in M also, and it becomes very complicated. A simple way to say it is simply that if machine productivity increases, what you want to do with machines also changes. The share that you want to do in machines also changes. But when you step back and you do static analysis of a one-time change in gamma or M, the analysis goes through, and I think that's what Ben focused on, and I'm now happy with that. So I won't talk more about that. I have another slide in case we have time, but it's not really worth spending time on. So the first thing I got concerned about, but then I decided that, again, that this is more complicated than I was thinking, was Ben alluded to a capital cost share of, existing capital cost share of 1/3 to proxy the machine, software, and AI share. I'm not sure where he got that, actually, but because I was pretty aware of the evidence, and I thought it was around 10%. So I went and looked, and I find the following. OECD data averaged across countries, and this is without the US to a great extent, because the US has not reported these numbers until very recently, essentially says that the capital cost share is 10%, and the labor share is something like 50%, and the other current costs, which are mostly correlated with labor because they're supplies and things like that, are 40%. If you look at the recent numbers for the US, I have the 2021 numbers. I think Ben had looked at the 2019 numbers maybe, I'm not sure. But in any case, they don't change over time. What you find is that the machinery, software, and IP products, which you could argue are part of that package, are at most 7% of R&D spending, business R&D spending in the US. It's even lower for government, by the way. There's probably some rental of capital hidden in the current cost. In fact, I'd be pretty sure of that. So it's got to be more than 7%, but it's unlikely to increase the number to 33%. However, much AI use in R&D is one-off own development by researchers, which means it's in labor cost, not in capital cost anyway. So that raises some more questions that I'll talk about a little bit later. But I will just tell you that some of his multipliers get smaller when you assume a capital share of 10%, and his theta equal -1, I have no quarrels with that, and you assume that machines could do half the tasks, which is what he assumes in the paper in his thought experiments. Whereas if you shift the share of tasks performed by machines completely to AI, that change, okay, the change in gamma, the productivity gain becomes enormous, 25 versus 2.25, because initially capital is very high productivity because it's cost effective. What he means by gamma is stuff that's cost effective. It's not just that it can do the task, it's cost effective at the task. And he sort of swept over that, but that's important. But its actual small share now is only 10%. So that means, essentially you get a huge productivity gain by shifting to machines. Okay, and this is my but. Right now, I think a lot of AI use in research is being programmed, executed, interpreted by research labor. So, in a sense, the higher share of AI, but there's a deeper problem here, which basically is that the survey evidence that we have on how do you use AI in your research shows that it's hard to separate the task. Just think about a literature search. if you throw, AI is very good at doing a literature search. You know, I'm sure all of you, many of you here have tried that. And however, you're going to process that and do things with it, and separating that into two tasks. Yeah, I can do that, but it's not clear to me that there's a lot of meaning associated with that. I copied a slide out of a paper by Chuganova and Harhoff and co-authors from the Max Planck Institute, where I was last week, and where they have surveyed researchers at the 1,700 researchers at Max Planck Institutes in Germany and the Fraunhofer Institutes in Germany. So both pure research and applied research, more development-oriented research. And essentially what they find, if you look through the list, you may not be able to see it, but an awful lot of this is to help write research manuscripts, to conduct literature reviews, to help with grant applications, to help write presentations. I even did that. I mean, my slides started out as an output of ChatGPT. I gave it my written discussion, and it gave me a nice outline, and so forth. So the point is that many of these tasks are the joint product of labor and AI. And it's really reinforced by reading that. So I spent some time in the paper, which will probably end up on the cutting room floor, given the space limitation, looking at the evolution of a research area that I knew well because I worked on it in the in the 60s, well, actually the mid-60s and the late 60s. And had watched evolve as it went forward, which was bump hunting in particle physics. Okay, looking for new particles, basically. And that has the advantage of the Z is kind of, at a broad sense, the Z has not changed. Now, at a narrow sense, of course, people created a different Z they were looking for. But at a broad sense, it hasn't changed. And it's basically the changes are mostly a response to advances in computing, which have been so substantial, although some of the changes are, in physical equipment inventions. So back when I was first working in this area, it was a human-centric process where you photographed the interaction and you took many photographs of interactions. Quantum mechanics says the outcome of the interactions is random, right? But it has a distribution. And you would, low-level technologists would actually physically scan the picture, and that would be turned into a computer program to fit, and so forth. And you looked at every interaction. What happened as the later advances was people designed equipment that could reject things they weren't interested in and only keep the ones they were interested in. You could have many more interactions as a result. I mean, you could look at tens of thousands, hundreds of thousands, instead of looking at several hundred interactions when you analyzed. And now people are using machine learning and AI for data analysis in the way of finding interesting patterns in the data. The Higgs boson discovery did make use of machine learning and AI. I have some cites in my discussion of all this. While this happened, the number of authors on a published article increased from a handful. I was on articles with like 4 people or whatever, to hundreds, where most of the page with the abstract is taken up by the list of the authors. You can have fun, going to look at PhysRev letters and seeing the list of authors for the Higgs boson article. Or sometimes the author's only listed as a consortium, because it's so large. Okay, the articles got longer and more detailed, much the way our articles got longer and more detailed over the same, 50-year period. And my point up here, with my lessons from the example, are first of all the diminishing returns, which is for any given line of research, as Bloom et al. Showed, and I think it's generally true. It doesn't mean there's diminishing returns overall. It just means for any given line of research, there's diminishing returns. As research advanced, the budget number of researchers increased. suggesting that, and indeed the Higgs boson was very hard to find. The moving target, I think that's important. The improvements in technology basically allow researchers to tackle more ambitious problems, which increases the complexity and cost of research, which means that, this fixed budget assumption, of course, is just not for a Z. As you progress, you basically, your appetite is created by the eating, so to speak. And this final thing is that increased automation didn't just replace human tasks. It created some new ones, such as a considerable amount of software design and development tailored to this particular activity. And much of that is still done by humans. Now, of course, some of that will end up moving to AI if it hasn't already, the software, but it's a new task. So I thought a little about, the examples suggest that AI's impact may be less about pure efficiency gains and more about enabling the pursuit of previously intractable problems. No news to anybody here, I don't think. I mean, I just want to emphasize it. The future research priorities, I thought about a few. I'm sure there are others. As Ben has suggested, detailed empirical work on the R&D task structures. The bottlenecks, in his model, the bottleneck is uniform across. That may not be a good picture, but, wonder what would happen if that wasn't. I suspect that, you go to Leontief, we're almost at Leontief already, and so it's still going to be the, the leaky, whatever. Dynamic models that account for expanding research frontiers. Just the dynamics in general, I mean, that was the problem I had with the gamma and the M, was basically that you can't do dynamics unless you recognize that M is determined by gamma, and gamma is determined by the underlying M's. I think the organization of research teams, that's the other thing that changed during this period, the evolution. And so that's right up with the labor papers we heard earlier tell you that same thing, this sort of change in the what skills are needed and what skills aren't needed as a result of AI. And this final question is whether this experience with computing enhancements, which we've seen everywhere, with the software enhancements, whether that really helps us inform us about the impact of transformative AI or economic enhancing AI?
Economic
No.
meaningful AI.
I've already forgotten it. But in any case.
All right.
Economically important AI. But basically the idea there being that transformative AI may be more powerful and harder to think about than just reducing the cost of floating point computations. Okay, thank you.
Thank you, Bronwyn.